Hello everyone on another video. We've progressed so far. We've done a couple of things, and just to do a quick, super quick recap. We've talked about injective, surjective, and bijective functions. Injective means that there's only one connection, one-to-one relationship, from A to B, and B um, can have isolated elements, like there is no connection between A to B. We've also talked about surjective functions in which all elements, there is no isolated element, all elements are connected together. And for the bi, there's only one-to-one relationship and all are connected. There's no isolation whatsoever. So as you can see, every B has some A, it can have many, but there's no empty B's, there's no isolated B's, while in this case there's only one link and there is an isolated B. Bijective suffices both cases. It's now isolated and there's only one link from A to B. So that we've talked about, and what else have we talked about? So yeah, we've also we were acquainted, we got introduced to there are two tests that you do in order to decide if there's it's a function or it's an injective function. So in order to have an injective function, you have to have a horizontal line crossing without crossing multiple points, crossing without crossing through multiple points. For a function to suffice, the vertical line test tells you if what you have at hand is a function or not, simply because if there are 2 points crossing the vertical line, then you end up having a non-function, just a mere mapping. The inverse function, the inverse was, I think, what we've stopped at the last time. So the inverse, you've got basically several approaches to decide on to come up with the inverse of a function. Primarily, one of which is that you change the you start off with the left to right, and then so for every multiplication, it becomes a division. So 2 over x, and then the negative minus 3. There's the algebraic method, which is way easier, in which you just like assume this is y equals to x plus 3. You take the 3 to the other side, and then you divide it by 2. So y minus so y1 minus 3 out of 2, that leads to the x. Basically, that's the inverse of the function. That's the algebraic way of deciding. Otherwise, you just flip like everything. And then you can see here that that's what you do. But I think the algebraic method is the most appropriate example. And this is the list of functions that you inverse with. So the positive becomes negative, the multiplication becomes division, 1 over x becomes 1 over y, whatever that is. Yeah, basically if it's a function and then y equates to f of x of y, the domain and the range interchangeably. The inverse of x squared is the square root of y, given y is not a negative number. And then the rest of the good stuff. I don't think we should memorize all this except maybe around the logarithm, the inverse logarithm being the exponential, and the a to the power of x being the logarithm of a to y. Yeah, alright, so that's that. And something you should consider at all times is the domain that the function operates on. So like if, for example, the square root of y, it has to be positive numbers, 0 plus natural numbers. It can't be real numbers. You can't consume everything. What else? Yeah, and this is also important because if you square roots, the negatives you end up by 4, but you can't go backwards. And this is the case here. It has to be for positive numbers. You can't like really go backwards. You can see we didn't get the negative, we got 2 instead of negative 2, just simply because we missed the domain. So this could be fixed by restricting the domain, as we mentioned. So no inverse. Let's see. Let's just see graphically what is going on here. Now, I said that this is quite important. This is really interesting simply because the use of graphs is like critical in linear algebra. And you'll get to see in machine learning in general that there is heavy utilization of graphs. Anyways, let us see graphically what is going on here. To be able to have an inverse, we need a unique values, okay? Just think if there are 2 or more x values for one y value, 2 or more x values for one value, so basically something like surjective function or normal function. How do we know which one to choose when going back? Yeah, that is correct. So it's like 2 or more values pointing to the same value. Yeah, that's tricky. There's no way. That's pretty hard to do an inverse here. Imagine we came from x1 to a particular y value. Where do we go back to? x1 or x2? In that case, we can't have an inverse. But we can have exactly one x for every y. So this is bijective. Bijective is the only thing that could work. Bijectives have inverses. But if we can have exactly one x for every y, we can have an inverse. It's called one-to-one correspondence or bijective, like this. This is important summary. We add it to the list of summaries. Good points. Yeah, I think we've added this here. And able to create images. Well, I think we're going to have a hard time with the images here on. Let's see if this is a copy image. Just something with the paste. Yeah. Looks like we're stuck. So there's no inverse here. Just get rid of this. And then the bijective function, just had to copy this, copy image. It's a great illustration if you ask me. Dismiss. Okay, so bijective functions have an inverse. Otherwise, you can't really go back, or you don't know which domain to go back to. So what is all this talk about restricting the domain? In its simplest form, the domain is all the values that go into a function which produce a range. As it stands, the function above does not have an inverse. Yeah, because the vertical test, you can have, no, this is an actual function. But it's not, I mean, it's not bijective, given there are 2 y values led to x's lead to the same value. This is a function, but it's not injective. It could be surjective, but it's not bijective. This function does not have an inverse because some y values will have more than one x. Y values can have more than one x, right? But we could restrict the domain so there is unique x for every y. So if you limit the numbers to like only this square, you'll end up having unique values, like what's been done here. So he has limited the number of domain values that could be opted, and now we can have an inverse. And now the inverse of this, and have an inverse. The function of x goes from the domain to the range. So this is, the function takes you from the domain, which is this one, from x's here to here to the y's. The inverse goes, what's wrong with my pronunciation? The inverse goes from f inverse of y, the range, to the domain. It takes you from here to here, while the original one takes you on the blue line. This one is the yellow line. Inverse. Let's plot them both in terms of x. Okay, so now it's f inverse of x, not f inverse of y. Okay. Not sure what's that mean. Let's plot them both in terms of x. So f of x here and f of x here. So this is f of x. Okay. F of x and f inverse of x are like mirror images flipped about the diagonal. So if you equate y to x, this is what you end up getting. Mirrors. The graph of f of x and f inverse of x are symmetric across the line y equals x. Example, yeah. Square and square root. Restrict the domain to only positive numbers. X square such that x is greater than or equals 0, or the square root of x such that x is greater than or equal to 0. If we try to take random numbers, for every x, like 0, you end up with 0, 1, 1, 2, end up like 4, then it's like 8, 9, 10. It's like there's this curve and then a straight line. The inverse of x squared is actually the square root of x. So if you plot the square root of x, then you'll end up having like 1 for every 1. 0, it's like 0, and then square root of 1. It's like, let me try to look for a tool that actually graphs things for us. Let me just pause the video and look for a tool. So here's a nice tool that we could use. So we have x squared and the square root of x. Let's plot x squared. Let's plot x squared. So there's a set of instructions that you could use here. So x squared is basically a to the power of b. So x squared, sorry, and then the range should be from positive. So let's just opt for 0 to 17, and let's plot this. So this is what we're getting. So positive numbers, and it's going upwards. Now, if we try to plot the square root of x for the same parameters, this is what you basically get. So this is the square root. It's been drawn like this. So it keeps adding things like that, and then they square it out. Now, x equals square is basically for every 1. If we could limit the range to say only 3, so 3 values, you could see like a bigger graph. It would make more sense. Like when you apply the 1 to both, you'd end up with the same results. The square root of 1 is actually 1, and the square root and the 1 squared is 1. So that's the 1. And then if you apply 2, let's like 4 on this scale. So on the blue one, then you should be getting 4 on 2. So 1, 2, 3, 4, and that's what you get. And the square root of 2, you end up with like 1 point something. That's that. And you could actually do this like square root of 2, so like 1.4, which is like almost half. And that's how you plot both, and then you end up with like, if you go like scale it like way, that's what you'd be getting. So the inverse of something is like a symmetrical thing. It's like a mirror. And then if you go like 20, the range is like 20 from 0 to the y. That's why we're seeing this like Now it should be symmetrical view. You can see, like, if you draw a line, you get like a mirrored view for both functions. And you could like get a better view, like if you go like 10-10, and then this would be like a better design, if I might say so myself. This is a really great tool that we could use to plot our graphs. So let's add this to our set of resources. Graphing tool, and that's that. So moving on, and this is what we get like in cases like, so it's almost like symmetrical on y equals x for 1 in this case. They are mirrored images of each other about the diagonal y equals x. Note, when we restrict the domain x less, which is basically zeros, less than or equal to 0, the inverse is then negative square root of x, which one inverse is 2, x squared negative greater less than or equal to 0, greater or equal to 0. So the inverse of it, this is a bit interesting. This is the inverse of this is the square root of x, but the domain is limited to negative numbers. So if you opt in for -2, negative like negative number, then you apply. Okay, it's bound to negative numbers. Like there is a way back, because for all x values, x squared, if you need, like if you take any value of x, then you square it, you get a given number, right? But if you want to go back, which is you want to get a negative number, so you square and then you add the negative to the, so assuming you have like, you apply into -2, so you end up with 4. So the square root of 4, if you go like 4 and then the square root of it, that's 2, but you apply the negative sign, that's -2, which is the inverse of what we've applied. Not always solvable. It's sometimes not possible to find an inverse of a function. Like in this case, a function of x sine. So if you take this one to the other side, that's sine inverse, and then multiply by 2, so 2 sine inverse. Why doesn't that work? We cannot solve for x. Why is that? It's like really weird. Let me try to apply on a paper. So x out of 2 plus sine of x. So we take sine of the end. Oh yeah, I see what you're saying. Because the sine of x here, like even if you take it to the other side, you can't really solve for x. Like, okay, be my guest equals like x equals what? 2 minus 2 minus sine of x, and you still have the x on the other side. So unless you go like 2 equals x plus sine of x, maybe. Why? I don't know. Just see this. Let's see what's being said here. Notes on notations. Even though we write f inverse of x, the negative one is not an exponent or power. It's just like a notation. It just means the inverse. So that's that. There's a difference between this way, and there's a difference between this and that. Okay, it's not this. Could just apply the same. Alright, so summary. So the inverse of f of x is denoted by f to the -1, and y we can find an inverse by reversing the flow diagram, or we can find an inverse by using algebra. Put y for x and solve for x. You may need to restrict the domain for functions to have an inverse, otherwise it's going to be a little tricky. Let's dive into the exercises. Alright, the first question. What is the inverse of the function f of x, fx minus 4? So we flip this with y. So y equals f5x minus 4, the y plus 4 divided by 5. Y plus 4 divided by 5. And you can see y has been flipped with the fx, and then f4 went to the other side, and then that's how you have it. Next question. What is the inverse of the function f of x? Now, I'm not sure if me doing it like on the fly is actually good for me, but I'll try to flip between the writing it down and solving it on a paper and just like theoretically solving it on the fly. What is the inverse of the function f of x? That's like the y. Y equals x squared plus 2, and this is a limited domain for positive numbers. So that's like natural numbers, for all natural numbers. Now this is quite simple because it's like y minus 2 square root of y minus 2. Now in this case is using the f of x, so that's like the inverse with domain. Now it has to be that y should be positive, and it shouldn't be like negative, so it has to be 2 plus 2 or equal. This is the right answer. It is right. So algebraically, so f of x is x squared. Subtract 2 both sides. This x squared equals, take the square root of both sides. Square root of y minus 2. Put for x equals, put f of inverse. Inverse equals square root of y. For x, we solve for x. We must take note that domain x belongs to positive numbers. F of x and the inverse. The graph for y, or f of x, is the half the parabola shown on the blue. This. The inverse is therefore the curve shown down, which is also half the parabola. Note that two curves are reflections of each other in the line y equals x. Therefore, positive. I honestly didn't consider the graph here because I can see that it starts on 2. You can see it starts with 2, but I don't think we will have enough time to actually plot this, but it's algebraically. It's like you don't want to have a square root of negative numbers, so you have to limit the domain. Alright, interesting. What is the inverse of the function f of x equals half? So you have like y equals half 3x minus plus 4. So it's like 2y equals 3x plus 4. And then it could go like 2y minus 4 divided by 3, and that's x. That's the inverse. What is going on? Yeah, I've done a mistake here because when you try to get rid of the 2, you multiply by 2, and you get rid of the 2 here. 3x plus 4. So what? Yeah, that's right. Okay, so 2y equals 3x plus 4. And then 2y minus 4 divided by 3. 2y minus 4 divided by 3. Yeah, that's the x. Oh, so what he's done is just factored out the 2. It's like he took the 2 as a common uh, denominator, like a 2, subtracted 2 from here, that's 1, y minus 2. It's like y minus 2. And what did I choose again? Did I choose B? Where did I get the 2 from? Like seriously, what the hell? What is the inverse of the function y equals log of ln 5x minus 2? Now the inverse is exponential of x. This is like where x is greater than or equal to 2.4. So we know the inverse of this is like the exponential of x. So if you go back to the inverse table we had, the algorithms, the equations or the functions. So the ln of y becomes, if n is greater than 0, a to the power of x. A to the power of x, e to the power of x. Okay, so does it mean that in this case it becomes e to the power of x? That's the L1y, power of x, e to the power of 5x minus 2, 5x minus 2. It's definitely 5x minus 2. It's definitely an e to the power of something. So these two are eliminated. So I'll be left with these. Ln to the power of inverse. Like if you inverse it, so f of y, so y equals ln 5x minus 2. So if we try to solve for the ones in the inside, it's like y plus 2 out of 5. That's not the right answer. Let's see how did they solve it. So we have log of 5x minus 2. So y 5x minus 2. Inverse the ln is e to the power of x. So e to the power of y. Okay, which equals 5x minus 2. Oh boy, so that's what this means. Okay, so it's like you apply that to the, let's take a look. Let's take a quick look. So x becomes the y of the other function. So ax becomes ln y, so it's like that. Okay, so we know that the inverse of ln is like e to the power of x, and then x is like what? E to the power of y, which equals, so where's the lingo, man? E to the power of x. inverse of log is e to the power of x. Alright, so that's like, so we have len of, so e to the power of x gives you len of y. Then we know y is like, so if you have e to the power of x gives you len of y. Then we know that len, we know that like y equals len 5x minus 2, right? So that's like, if you like the exponent, if the exponent is flipped, you get the len. If the len is flipped, you get e to the power of x. So the power of x gives you that inverse. Like, just take a step back, and the x squared gives you the square root, right? So x squared gives you the square root of like y, right? So that's the inverse. The inverse gives you the square root of x, right? And e to the power of x gives you the len of x. Is that it? Here's another example just to give us like a quick understanding. So to find the inverse of y, len x plus 1, now this is y, and then we know the inverse of len is e to the power of x. So if we have like, I'm trying to solve this without looking at the answer, so just trying to get a better idea of how things work. So ln x plus 1, so that's that. So we know that this is y. The inverse of len is e to the power of x. E to the power of x. So if we switch the, look at the answer. So y equals ln plus, so if we switch the values, x equals len y plus 1, then we go like, if we apply, so ex equals e to the power of l, and y plus 1 e to the power of ln yields, eliminates that. So if you go like, just 1 second. Now here's the example I was telling you about. So if you can see the following is true, the len of ex exponent of x equals x. So this len and e actually cancel each other out. So you have e to the power of ln x. They actually cancel each other. So the e to the power exponent of ln, they cancel each other. You remain with an x. So in both these cases, that's the deal with the natural log. These are the properties of natural log. So you have ln AB, ln plus ln B, ln negative, and ln A to the power of n. You can take the n to the other side, and log of A, log of A. And this is exactly, this is the key here. This is why, let me copy this image and edit the log properties. Just get rid of the highlight. And prop. So ln e to the power of x equals x. Why is this? Because the reason behind this is that x goes before ln e and ln e cancel each other. That's how it is. So if we go back to the set of examples we had, where is it? Yeah, so in this case, you flipped, so if you apply e to both sides, so that you would get rid of the ln, you apply e to the power of x, e to the power of ln, y minus 1 would lead you to ln e to the power of ln. They cancel each other, so you'll also remain with ln. So this is also true for this. So you can, where is it? This here is important. So we need to add this to the list of nodes we have. So each other, and also okay, that's that. So we can explore more on this, but like e to the power of x. So if you need to find the inverse of this, you need to practice exercise. You need to find the inverses of all of these. The power, this is basically x to the power of x minus. Tricky. I need to do more exercises on this then. I'm not very familiar with the log and all, so I think we'll come to this if I think we need it. But let's stick to the inverse for now. This is a nice tool. Back to the set of exercises. So in this case, in this example, we have ln 5x points to. So if we apply, in this case, the ex to both sides, e to the power of x equals e to the power of ln. E and ln cancel each other, so the power of x equals 5x minus 2. And then you just work arithmetically on this, algebraically on this. That's what you get. Alright, so what is the inverse of the function x squared? Paper. So you have y equals x squared cubic plus 5. I need to find the inverse of this. So we need to y minus 5 equals x cubed. And if I'm not mistaken, the inverse here, x to the power of n, that's like square root of n out of y, so that's the cubic square root of n. And so you'd be like cubic square root of y minus 5 equals x, so that's the inverse. And it has to be that the values under the square root 0 and plus, so that's 5. It should be bigger or equal to 5. The mains x equated are greater than 5, that's for sure. What did I do wrong? Yeah, so y minus 5, the main are real numbers. Oh, so that doesn't matter for this cubic square. So it's only for the double. Minus 3. Let's plot them both in terms of x. Try to find the inverse. Restrictions of each other. Note that in this case there are no restrictions at the main range. Should note this down. not even number. Not. Let's try to solve for square roots. Yeah. What is the inverse of the function? So we know that from the list of functions going back leads you to the x to the power of n being n being the number on the square root. So this would be x to the power of n. X to the power of n would be x plus 2 to the power of 3. I need to plug it. 1 second. So yeah, I was saying x to the power of n basically eliminates. So x to the power of n becomes n to the power of x. So in this case, it becomes x plus 2. The inverse of this is tricky. X plus 2. Now let me try to solve this on paper. So we know that x to the power of n would lead to n squared root of x. Now we have the cubic square root of x plus 2. Now this is assuming x plus 2 is y. So we could go like, now why is this not to the power of 3? This is what's really confusing me. Why is the 2 not included? It's x to the power of n, right? What's going on? Let's see. Let's just choose any random number. Sorry, a is the right answer. X minus 2. Did it solve? Of course, man, it's like x plus 2 cube. So cube both sides. Y cube equals x plus 2. Subtract 2 from both ends. Y cube minus 3. That's, oh man, this was very simple. Cube both sides, man. What the hell is wrong with you? It's like weird. I mean, the other example was a bit confusing to me, maybe. If we go back, just go back. I'm not sure if this is. So this is the 6th question. Let me try to, no, sorry. So let's go back to the 5th question. So x cubed plus 3. That's like x cubed plus 3. We know that the inverse is like, so y equals x cubed plus 3. Is that plus 5? Yeah, so we take the 5 to the other side. It's like y minus 5 equals x cubed. And the x cubed is like the square. Y minus 5 equals x. Man, what have I done wrong? Why can't I solve it now? And then cube doesn't really matter, so it's all still wrong though. Yeah, look at the number of faulty answers I've done. That's terrible. Alright, I still got a chance though. I need to solve all these correctly. So in this case, what is the inverse of the function? So y equals x squared minus 3 for x less than 0. Less than or equals 0. So let's just y plus 3 equals x squared. So that's the square root of y plus 3, that's equals x. And then we need to suffice the domain. The domain has to change. It has to equal greater or equal to minus 3. Greater or equal minus 3. Again, how is that? So x plus 3 equals x squared. And then we swap, yeah, we've done all of this right. So the square roots. So does it mean that it has to be, it didn't say here, that the square root is either positive or negative, man. It's always positive, right? Like seriously. Okay. Oh man, this is frustrating. The inverse of fy equals to y plus 3. Okay. However, must ignore the domain. Now this is all correct. I mean, till this point without the negative and positives, it's completely fine. Now why did it become it's less than negatives? So the domain that goes in, you should be able to go back to it. It's negative 0, right? It's negative, so you have to apply the negative in the front. Huh. That is why. What an idiot. Focused. Which of the following correctly shows the inverse of the function shown above? Inverse of the function shown above. So it has to be like this way. Good try, but C is the right answer. The graph functions inverse are always reflections of each other. The y line. Where's that y line? So how do I know the line is not in here? It's not like here. Oh, it's a slope. It's a slope. So there's no slope here. There's no slope here. There is a slope here. What is the inverse of the function? So that's minus 4. X greater than or equal negative 4. Has to be negative 4. So we're limiting the domain here to negative 4. What is wrong now? I think I'm about to. I basically gave up, which is not good. Damn, that's nasty. F of x plus 4. X is, for values x greater than or equal negative 4. This is exactly the same as the function. Equals or greater than negative 4, right? This is really confusing me. Alright, so x plus 4. X is plus 4. That's fine. Absolute of x plus 4. For values x greater than or equal negative 4, that's like 0. If you apply negative 4, it's like 0. Then if you apply like negative 3, it's like negative 3, that's like 1. Yeah, so that's like, it's always positive in that front. Put y for f of x. Okay, and then you solve for, you take for the other side y minus equals x. That's fine. But the problem is with the domain. For all positive starting from -4. So let's plot them in terms of as it is now. So this is the f, starts from negative. If you apply -4 to the maze, how is that 5? Array is a line with a start point but no end point. It goes to infinity. The inverse, therefore, the ray in red. Note that the two rays are reflections of each other in the line y equals x. Therefore, with the domain greater or equal 0. I'm not really clear on this. Why? Calm down. Let's go to the next question. I need to revisit all of this again. So y equals 1/4 e to the power is the power of x minus 3. This would be the inverse of this. Alright, so 4y equals e to the power of x minus 3. 4y plus 3 equals e to the power of x. For can't have negatives. Okay, so 4y, that's fine. I've done all of this. This is correct till here. I've done this. You have to take the log base. This is what I've done. Ax equals len, done this. This is exactly what I've done. But why? Y plus 3. X plus 3 is right. But why? Let's plot them. Like, can you only know the domain using the plot? It's like super weird. Is the exponential curve in the blue? Okay. Is therefore the logarithmic curve shown in red? Okay. Reflections of each other. Fine. However, logarithms are only defined for positive integers. Yes. So how come you're solving for x? Oh man, that was simple. Oh man, that was like super easy. Check out the quiz result. 65% to earn a medal. Oh man, I need to redo all of this, but I need to set my mind. It's like my lack of knowledge in a proper lack of knowledge. So this is basically a lost. I'm saying it's a lost case, but I've lost this one. I don't think I've completely grasped the idea of inverses. Otherwise, I would have scored well. I've seen that much of the exercises revolve around the logarithm and the domain of those variables. So I'll have to revisit this whole thing again. So let's hope we've learned stuff from this session. and then we will apply what we've learned on the next session. We can't redo the exercises now, given we've already know the tips and tricks. So we'll wait it out then. Alright, I'll see you on the next video.